Let's now do some examples and practice plotting impedance points on the Smith chart and using the chart to convert between impedance and reflection coefficient. So every point on the Smith chart is an impedance and a reflection coefficient at the same time, and you can use the chart to convert between the two. So for point A, let's say that we have a load impedance which is equal to 150 plus J50 ohms. The first thing that we have to do is we need to normalize this impedance, and since we have a 50 ohm Smith chart, we're going to normalize to 50 ohms, resulting in little za equal to 3 plus J1. And so our job, or our goal, is going to be to find gamma, the reflection coefficient. And in order to do that, we're going to plot 3 plus J1 on the Smith chart. So little r is equal to 3. Again, that means that the real part of the normalized impedance is equal to 3. So here's our r equals 3 circle. Now let's find our plus 1j circle. Here it is in blue. And the resulting impedance point, 3 plus J1, is going to be the intersection of these two circles. And the reflection coefficient, gamma A, is going to be a vector from the origin to this point. Now, to find the angle of gamma A, we extend the vector to the angular scale. That's the angle of the reflection coefficient in degrees scale. And we find that the angle is right about, let's say, 15 degrees. Now to find the magnitude of gamma A, I'm going to use the ruler at the bottom and imagine that I can transfer the length of gamma A down to the scale and find that the magnitude is equal to 0.7. Okay, so let's say that that is the case for this particular example. So now I found both the magnitude and the angle of the vector gamma, and that's it. I've used the Smith chart to quickly plot my impedance point and then basically read off gamma, the corresponding gamma, which in this case has a magnitude of 0.7 and an angle of 15 degrees. So now let's take point B to have an impedance of 25 plus J20 ohms. So again, I'm going to normalize that to my 50 ohm Smith chart. And I'm going to now see where the r equals 0.5 circle intersects the x equals 0.4 circle. So here is the r equals 0.5 circle. Just going to draw the beginning part of the circle. And here's the x equals to 0.4 circle. So there's the intersection, and there's the vector gamma B. And again, I can extend this vector to the angular scale to find the angle or the phase of gamma B to be 125 degrees. So there it is. I found that the reflection coefficient that corresponds to 25 plus J20, gamma B is equal to 0.4 and a phase of 125 degrees. Okay, now let's move on to point C. Now this time I'm going to specify a gamma, and from the gamma I'm going to find the corresponding impedance. Okay, so I'm going to use the Smith chart to find the impedance ZC. Okay, my gamma is equal to the vector with a magnitude of 0.5 and an angle of minus 100 degrees. So I'm going to have to find where is the angle of minus 100 and extend that to the origin. And then let's just imagine that I use the scale at the bottom to find the magnitude of gamma C. Now I'm going to draw the closest constant R circle to this impedance point, and this circle has an R equal to 0.55, and then I'm going to draw the closest constant X circle, which is right at 0.7. Okay, so I again plotted my reflection coefficient gamma, and then I found the closest constant R circle and constant X circle that's right in the vicinity of this point gamma. And it turned out that my normalized impedance is equal to 0.55 minus J0.7. And to get my actual impedance, I have to multiply by 50 ohms. Let's move on to point D and say that it has a reflection coefficient equal to a vector with a magnitude of 0.8 and a phase of negative 20 degrees. Okay, so let me find the minus 20 degree angle on the Smith chart and extend it to the origin. And then along the dotted line, I'm going to draw a length of 0.8 and call that my reflection coefficient vector, gamma D. So now I have to find the closest R circle to this point, okay? And that R circle looks to be right around 2.6. And then I'm going to find the closest X circle, which is X equals to 0.4. Oops, I keep writing J, meaning to write X. Okay, so X is equal to 0.4. No, actually, I'm sorry. X is equal to -4. Okay. So I found the normalized impedance corresponding to this particular gamma to be 2.6 minus J4, and then I can multiply by 50 ohms to get my actual impedance. Okay, let's now talk about how to move on the transmission line using the Smith chart. And moving will mean that my reference plane moves farther away from the load impedance. So let me draw a circuit where I have a load impedance, ZL, and then my generator is going to be a distance L away from the load. So the generator is going to have a source or generator impedance equal to ZG, and a voltage, ideal voltage of VG. Okay, so this is my load, and that's my generator represented by VG and ZG. Now looking into the load, I'm going to see a reflection coefficient of gamma L. And I know that if I move L away, then the magnitude of my reflection coefficient is going to stay the same, and the phase is going to decrease by 2 beta L. So this is my new gamma in, and I can use the Smith chart to draw the reflection coefficient gamma in and find the corresponding Z in. So every point on the Smith chart is a vector representation of the reflection coefficient gamma. And moving on the Smith chart implies rotating gamma clockwise because we're moving away from the load towards the generator by an angle of 2 beta L while keeping the radius of gamma the same. Now given a vector gamma, let's say that I rotate it all the way around the Smith chart, so 360 degrees. That implies that I've moved a distance of lambda over 2 away from my load, because the phase of gamma has changed by 2 beta L. 2 times beta times lambda over 2 is equal to 2 pi. Alright, let's zoom in and take a look at the circular scale on the Smith chart again. So this scale not only gives you the angle of the gamma vector, but it also, the very outer scale here that I'm going to highlight for you, gives the fractions of wavelength that you've moved away from the load and towards the generator, implying that you're moving clockwise on the Smith chart. Okay? So let's say that a gamma vector has rotated all the way around the Smith chart, and you've started at 0 wavelength, and now you're coming back around to 0.5 lambda. Okay, because you can see the numbers 0.47, 0.48, 0.49 are approaching 0.5. Okay, so before doing some examples to illustrate these new concepts, let me just take a little time to describe how to add series reactants using the Smith chart. So let me draw up a little circuit. We have a load impedance. I'm just going to write down the normalized impedance equal to RL plus JXL. And then in series with a load, I will add an inductor with an impedance of plus JX. Okay, so looking in after the inductor, I will see an input impedance which will be equal to RL plus J multiplied by the sum of the two reactances, XL plus X. Now you can see that as I've added the inductor, the real part of the impedance has not changed, while the imaginary part, the X, has changed. So what that means is that on the Smith chart, I'm going to be moving on a constant R circle. Okay. While my X is going to be changing. Now let's just illustrate this point with a little example. Let's say that I have a normalized load impedance that's equal to 1 minus J. Okay. So I know that that impedance point has to be on a R equals 1 circle, and it also needs to be on a X equals minus 1 circle. So let me find, so the X equals minus 1 circle is that one right there with a dashed red line. And the point of intersection is of course that black dot that I drew. Now let's imagine that I'm going to add a series reactance equal to plus 0.4 J. That means that I'm going to move from X equals minus 1 to X equals minus 0.6. Okay, staying on the same R equals 1 circle. So here is my X equals minus 0.6 circle. And I got there by adding plus 0.4 J to the original load impedance of minus J. Okay, so now let me erase all this stuff so that we can work through a couple of concrete examples to put this knowledge to practice. Okay, so in example 1, I'm going to draw a little circuit starting with a load impedance as always. And this load impedance is going to be equal to 15 plus J15. And we know that in order to plot the impedance point on the Smith chart, I need to first normalize it to a 50 ohm Smith chart. And then plotting this point, I can immediately read off the Smith chart the reflection coefficient vector, gamma L. Okay, now I'm going to insert a transmission line section with an electrical length that's equal to 0.3 lambda, where lambda is my wavelength. Now I know that when I rotate on the Smith chart, my gamma vector, the magnitude stays the same, and the phase changes by -2 beta L, right? So my gamma in is now equal to gamma L, and then e to the -2j beta L. And that has a corresponding input impedance, which is really what I'm trying to find here. And I'm going to use the Smith chart to get that answer for me. So the first step is to plot the impedance point, the load impedance point. So my normalized load impedance, remember, is 0.3 plus j.3. So this is my r equals 0.3 circle, and it intersects the x equals plus 0.3 circle right at that point right there. So this is ZL, and then drawing a vector from the origin to that point gives me my gamma L. Okay, now I'm going to extend the gamma L to the outer circular scale in order to just note my starting point, because I know that I'm going to be moving on a transmission line away from the load and towards a generator. So my starting point in wavelength is right about 0.05 lambda. Okay. So now my job is to move by 0.3 lambda towards the generator, which of course implies moving clockwise or rotating clockwise on the transmission line. Alright, so if I'm going to add 0.3 lambda to 0.05 lambda, I'm going to end up at 0.35 lambda. Okay, so I need to find this point, 0.35 lambda. So I rotate and I rotate around and around until I end up at 0.35 lambda. It's right about there. Okay. Alright, so that's 0.05 lambda plus 0.3 lambda. Now, if you actually have a paper Smith chart, this is where a compass comes in real handy, because you can keep the radius the same and then just rotate around the Smith chart. So I'm going to just imagine that I had such a compass on my computer screen, and that I was able to keep the length of the gamma L vector the same, and then rotate by a total of 0.3 lambda. Alright, and then I ended up right there. And this would be my gamma in vector now, and that impedance point there is of course Zn, which is the impedance point that I'm after. So let's say I used a compass to rotate by 0.3 lambda clockwise on the Smith chart. Now I should read off Zn directly from the Smith chart, and I can see that it's very close to the r equals 0.7 circle, and also very close to the x equals plus 1, no, minus j 1.15. Alright, so I've just moved on the Smith chart starting from a particular gamma L, and I've rotated by 0.3 lambda, and I ended up at gamma in, and then I use the Smith chart to read off the impedance. Alright, and then the last step is to just multiply that normalized impedance by 50 ohms to get my final impedance. Okay, so now let's do example 2 and get a little practice adding a series inductor to a load impedance. So the load impedance in example 2 I'll denote as ZL2, and it'll be equal to 0.2 minus j 0.6. And then to that I will add an inductor, which at a given frequency will have a reactance equal to plus j 0.8. Okay, so then the impedance looking in after the inductor is going to be equal to, I'll denote that as Z in 2, and that'll be equal to 0.2 plus j 0.2. So the real part has stayed the same at 0.2. And I've just added the x's, the imaginary parts, together. Okay, so step 1 is to plot the normalized load impedance, which is equal to 0.2 minus j 0.6. So I'm going to need to find where does the r equals 0.2 circle intersect the x equals minus 0.6 circle. And that's going to happen right there. Okay, so that is my ZL2 point. And now, staying on a constant r circle, on the r equals to 0.2 circle, I'm going to add 0.8x and end up at plus 0.2x. You know what? I was not actually on the r equals 0.2 circle. So let me just fix that. Okay, move that point over. Now I'm on the r equals to 0.2 circle. Okay, so let's try this again and move by 0.8x and end up at plus 0.2. Okay, and so that's my input impedance point, and I can just use the Smith chart to read off the numbers. It's equal to 0.2 plus j 0.2. Okay, so there you have it. We got some practice using the Smith chart. We were able to plot impedance points on the Smith chart, vectors, and I just noticed a little mistake here. Since I wrote capital Z, we need to multiply the normalized impedance by 50 ohms. And we also learned how to move on the transmission line using the Smith chart and how to add series reactances.